So let's look at designing a test. The test procedure is designed in such a way that the probability of the type 1 error occurring is contained, as I just said, in a small specified value equal to alpha. For every test, we will choose a test statistic that provides the relationship between an estimator and the parameter about which the hypotheses are proposed, and the distribution of this test statistic will be known. Designing the test consists then of identifying the critical region where this is the set of observed values of the test statistic that will lead to rejection of the null hypothesis. Now I'd like to draw this. Suppose we have a population which is centered about a mean, normally distributed. Now let's say, for example, that we are a cotton rope supplier. And we have a random variable, x, which is the strength of the rope. Okay. Now, given that the strength is a random variable normally distributed with mean mu0 and a standard deviation, we have a new supplier coming along, and he says that his rope is stronger. This means that he's claiming that his rope has a higher strength, where mu1 is greater than our mu0. So now we want to set up our hypothesis so that we set HO as our status quo, our hypothesis, our null hypothesis, and the claim that the supplier has a higher strength of rope is the alternative hypothesis, or H1. So in this example here, we can see that there's an overlap of our two distributions in this area here. What we're going to do is to take a sample of our supplier's new rope to get a point estimate for the mean of the population. And this point estimate could lie anywhere around the mean with a probability according to the normal distribution. And we will choose an alpha level such that the probability of the type 1 error occurring is contained within a small specified value, alpha. And this means that the probability that we will accept the claim of the supplier and reject our null hypothesis, when in fact the null hypothesis is true, this means this will have a very small probability. Let me look at this again now. So let's look at the hypothesis test for this example concerning the mean of a normal population when the standard deviation is known. So how do we do this? So we first set up our test as follows. The null hypothesis H0, we set mean equal to mu0. We hypothesize that our mean is equal to our current mean, mu0. Our alternative hypothesis H1 is set up to reflect the claim. And that means if the mean is not equal to mu0, then it would be, in this case, greater, because we're looking at the strength of rope, and the claim is that it's greater. Now we take a sample, and we calculate, as we did before, a test statistic. Now, in this case, we're checking the mean of the population, so we calculate our x bar. Now, sigma is known, and as our parameter x is normally distributed, we do our transformation. We subtract the mean, or the mu0, and we divide by the standard deviation, which is sigma over the square root of n for our x bar, where n is the sample number, the number of articles in the sample. And we know that this normalized test statistic is distributed with a mean equal to 0 and a standard deviation equal to 1. So this should sound very familiar. This is exactly what we did in the last section. So here I have drawn then the picture of the test statistic z, so z observed, equal to x bar minus mu 0 over this sigma over the square root of n. Now what we want to do is to compare our z observation to z alpha. This is the critical value of the statistic. And this I've drawn down here. The values in the distribution of the test statistic beyond z alpha here constitute the critical region. And in this case, the critical region is chosen as the set of all observed values of the test statistic that are greater than z alpha, where the probability that z observed is greater than z alpha is equal to a small value alpha, which is here, the probability. So with the given H1, the given alternative hypothesis, we will reject the null hypothesis in favor of the alternative hypothesis if our observed z is significantly large enough. So we draw a line here at the z alpha such that the probability of a type 1 error is limited to this very small number alpha. Now what does this mean? If the null hypothesis is true, then the observed value of the test statistic will be a value from the z distribution, most probably near the mean, near 0, because that's where the probability is the highest, if the null hypothesis is true. If, on the other hand, the alternative hypothesis is true, then the observed value will be a large value falling somewhere to the right of 0, on the higher side for this case. And we have drawn a line then to determine how large is too large in order to decide if the null hypothesis should be rejected in favor of H1. Now, wherever the line is drawn, there will be a probability that HO is rejected when, in fact, it is true, because, of course, this random variable z can kind of take any value, a very large value or a very small value, even if its mean is 0. But we draw the line such that the probability that it falls in the critical region is very small. This line is drawn then at z alpha, where z alpha cuts off at a probability at the upper tail in the z distribution equal to alpha. Let's do an example of our rope supplier, and then I think this will all be clear. So, a supplier of cotton rope claims their new product has an average strength greater than 10 kilograms. A sample of 16 rope pieces gave an average of 10.2 kilograms. If the standard deviation of the strength is known to be 0.5 kilograms, then please test the hypothesis that mu, the mean of the population, is equal to 10 versus the mean of the population is greater than 10. And do this to an alpha equals 0.01 level of significance. So the first thing we need to do is to set up our hypotheses. So H0 is going to be then mu is equal to mu 0, which equals 10 kilograms. Our claim that our average strength is greater than 10 kilograms is H1. Mu is greater than mu 0. Now we need a test statistic for this. We're looking at the mean, so we want to look then at x bar, and we have an x bar value of 10.2 kilograms. Our z observed we normalize this as x bar minus mu 0 over the sigma over the square root of n. We get here then 10.2 x bar minus 10, that's mu 0, over the known sigma, which is 0.5 kilograms, divided by the square root of 16. If you do this, you get 1.6. Z obs equal 1.6. Now, we need to now find our Z critical, or we called it Z alpha, where alpha equals 0.01. So to do this, we look in our normal tables. So for alpha equals 0.01, we need to have then a probability of 0.99. And we can see that our probability is going to lie somewhere between these two values. So we have z equals 2.32 and 2.33. In actual fact, if we did this with a computer, we would find out that the exact value is z alpha equals 2.326. Now we look at it in a graph again. So here was our distribution of z observed equals x bar minus mu 0 over sigma over the square root of n. Z critical was 2.326, and what this means is that the probability of being of a z value that's greater than z critical is equal to alpha, which is equal to 0.01. Our z obs, if you remember, was equal to 1.6, which we show here. So now what do? Do you reject the null hypothesis? So H0 mu equals mu 0. Or H1, do you accept the alternative hypothesis? So again, this is here the null hypothesis. What we observe that z obs is not in the critical region. It is not greater than 2.326. So we cannot reject the null hypothesis. The mean strength of the population of cotton ropes, even though it came from the supplier who made the claim, it's not greater than 10 kg. We cannot say that to a significance level of 0.01, and we say that the supplier's claim is not valid. So I hope that was clear. There are different types of hypotheses. The selection of the critical region will depend on what exactly you're looking at. And here are 3 examples. These are 3 cases that are encountered normally in practical testing. And so we have then case 1, where we have the null hypothesis is that the mean equals our given mean, our current mean, and hypothesis 1 that the mean is less than our given mean. And here we believe that the mean is less than the hypothesized value H0. And so here our critical region then is to the left of our 0 value. As we had before, case 2, here we're looking that we believe that the mean is greater than the hypothesized value. This is the same case we just did. And here we would set our critical region then to the right of 0. So in the third case, we don't know. We don't know if we have a value that's higher or lower than our known mean, our current mean. So we believe simply that the mean does not equal the hypothesized value of H0. And so here we have to look on both sides of the 0 value. And in each of these cases, the test statistic will be the same, but the location of the critical regions, as you can see here, will be different.